私の2週間の研究報告。日本語まだ上手です。これから。
大きな声で言って聞こえない。大きな声です。
すみません。これから今英語を使います。Today my topic is multiplicity of linear system based on space norms. When we talk about multiplicity, in my previous paper, I used the Busa kernel and Riemann function to distinguish the multiplicity of intensity lambda. But in reality, how to define the Ju equal to lambda, Ju equal to Ju lambda is very hard. So it takes a lot of time, day and night brainstorming. Until the stochastic process that takes place with the time t. The notation of multiplicity is significant for the expression of the complex randoms of linear random functional. For Gaussian case, the multiplicity has been discussed to some extent. We recognize the significance of this notation by observing some simple example. First of all, we can say a very simple example like this process is like this P1 plus P2, and we know the multiplicity is true. And they have the same intensity. So we naturally require to consider the multiplicity of the process. First, I will introduce some previous introduction. We are interested in the random system that is expressed as linear functional as a new noise depending on space parameter that takes place in place of the time t of stochastic process. We've been motivated by the decomposition of the process that we claim the intensity of proton process discriminates their type. And like what we said, how to define the Uj is very brainstorming. It takes a lot of time. yes. But therefore we can take the span, the span U of lattice type distribution in order to discriminate them. As a result, we are linked to consider the linear system and are naturally linked to consider the multiplicity. Note the notation of multiplicity is very well known for the second order process in the Gaussian case. We'll give a definition which is standard extension to a case where the Hilbert space technique is not applicable, which means we don't have the, we can use not by by the L2 topology, but by the limit in the limit in distribution. So, but don't worry about that. We can use the correlativity function to investigate it. We claim that the intensity lambda of proton process to discriminate the type. And next, we will come to the space noise P dash lambda. The space noise P dash lambda, first we come to the proton process T and lambda. The T and lambda, like a good friend, but in reality they are dual pair in this process. So start with the proton process P lambda. T is belong to the whole R1, and lambda is from 0 to infinity, and P0 lambda is equal to 0. For the P lambda, the convergence of PT lambda is limit in rho, which is limit in distribution. Like what we just mentioned about, we cannot use the Hilbert space technique. The L2 node cannot be used. So we use the correlativity function to characterize it. So, and we consider the correlativity function of phi u, phi z. The phi z is the log of the phi z. So it's like the lambda t product EIZ minus 1. So the lambda t, they are dual pair. And the dual pair lambda t, we can easy to see it's the one-dimensional inner product. That means lambda t is one-dimensional inner product. So it can be a product in its turn. And in a sense, lambda and t, they have the dual relation in some sense. Now we consider the time t. The time t, we can do the shift of t. The shift of t. And t can be t plus h. And we can consider the dilation of lambda. Dilation of lambda. From lambda to a lambda. When we come to the proton noise, P dot T1, we can discuss function of P dot T and start the analysis use the L2 node. But P dash T can use the L2 node, but P dash lambda cannot use the L2 node. So, and P dot lambda has the same similar manner in the Gaussian case. We can deal with how to compute it. When P dash lambda is an abbreviation of P dash 1 lambda. It's another noise. We can say it's space noise. It came from Levy's work. It's from the reference Levy's 1934 paper. above we say T and lambda, they are dual pair, but we know the T is from minus infinity to infinity, but lambda is from 0 to infinity. One is the whole line of the real line. Part of was the half space of the real line. So actually they are a little different. As we come to think about the stochastic process, P lambda, P dash lambda is independent and every lambda from the Gill form, which say the C cos C1 plus cos C2 can be the product C cos C1 product C cos C2, which means the characteristic functional can be separate. Firstly, we observe integral. It looks like integral, but actually it's a polynomial. For the summable series, we can consider the characteristic functional. It's the phi zeta. Phi zeta can be expressed as the exponential of the expectation. And because independent, so we can write it from the summation to the product. Because the independent, we can write it as this one. And after a serial computation, we can get the result is the explanation of this term. In the theory, if the measurable function f lambda is integrable on the 0 to infinity, then the integral exists and its characteristic function phi zeta is also exists. And the phi zeta also follows from the Bochner-Minus theory. The most important of Bochner-Minus theory, it must to check the positive definition. So if you want to check the positive definition, you can we must have this term be positive. And from the formula, we can know descriptive definition. So the corollary is if the bizettel exists, so the secrecy, the characteristic functional also exists, and it also abetted by the Faulkner-Miller theory. What we have in mind on the space parameter lambda is that lambda corresponds to the intensity of proton process, and lambda discriminates the type of distribution of proton type. Although lambda is significant in the sense, however, we know it's not visualized parameter. Lambda is mere 9. We must introduce the variable u. It corresponds to the jump of the proton process, and it's also called the span of lattice type distribution. And we should determine the uj equal to uj lambda. And as I mentioned about the how to define the uj equal to uj lambda is very hard, so it takes a lot of time and a lot of brainstorming. So how to define the uj equal to uj lambda is closely related to determine the multiplicity. And we can see the page 14 and page 15 have two examples. The first example is what the example like what I mentioned about, if the alpha is irrational number, so we can see the multiplicity is 2. It's come from the Professor C's example. And next on the page 50. We can see the stable process. The stable process, it has from this stable process, we can see if u if u is greater than 0, then we can see it's from up, and if u is less than 0, it will below under the alpha ratio, like this sign. So we can see the multiplicity is also 2. We should define the integral. In reality, it's a linear functional. F y lambda. Where y lambda is a linear process of lambda, which is the linear polynomial of p dash mu after some assumption of lambda mu As we come to the double multiplicity, the linear system can be classified by the type using a flying group, and the single class could be investigated by the change the lambda 0 to lambda 0 e to the du. And next, we want to introduce a very important group. It's a phi group. Our linear correlated system can be parameterized by lambda greater than 0, so that it's natural to think of an action due to the transformation group acting on the U. First of all, we take a dilation. As what I just mentioned, the dilation is from U to AU. And what I mentioned is about lambda to A lambda. But now we consider the jump U to be dilation. In the case U is from 0 to infinity, it seems to introduce the one parameter group of dilation, so that we introduce the tau s, the action from U to e to the SU. And that is satisfied the property, the tau s product tau p can be tau s plus p. When we come to the action of tau on intensity measure, so we can see this. The interesting property can be seen in the dilation is U to the U product e to the t. Then the parasitic function c to c can change into the new form if we change the parameter like to the ESU. So namely, the intensity change from the lambda U ES to the lambda V E minus S. But we know the distribution also remains the Poisson type. A Poisson distribution might be considered to be a simpler compared to the Gaussian distribution. In some cases, may not so, but not quite. Note that the characteristic function is by two parameters. The one is intensity and second the space parameter, and the second is the scale. And in the page 18, you can see a proposition. It can be see the tau s invariance. So it's intensity do some action, it can still remain the Poisson process. And we also know that the very famous one is Gaussian process. B dot t is time parameter, and another one is Poisson process. P dot t lambda. And also, in this case, we consider the t to the t plus h is the shift of time. And in the space noise, we can only consider about the dilation. We should discuss noise with the space parameter. It has been established that the basic noise depending on space parameter according to a law of small probability. It's the standard Poisson noise. And next section, we want to introduce some Professor Thesis approach and the definition of multiplicity. When we come to the lattice type distribution, it could be characterized by the semi-invariant. The semi-invariant is corresponding to the moment of probability. And here the kappa 0 is D0. The semi-invariant has this form. We have the cosine function such that the cosine theta equal to the log of phi theta. And because the semi-invariant has this form,
kappa, kappa is semi-invariant type. Semi-invariant.
so we can compare it to the Poisson distribution. So the kappa n always equal to the constant because the kappa n always equal to lambda compared with the Poisson distribution. In the Poisson test, as what I mentioned about, the kappa n are always constant. Then the generating function of the Poisson system will be generating function will be this term. And minus 1 is only contribute to kappa 0. So we can a little omit it. Therefore, we take the lambda et to be representation, and we can modify it to be the lambda e to the tu, and the u is the span of lattice distribution. Finally, we take the lambda e tu and make a cache of action on it using the affine transformation. The affine transformation is